Okay, so in the last video, we looked a bit at the stepping action class and saw how we can see particle information for every step that the particle takes. So remember, a step is just every time a particle interacts or has a process occurring, or whether it enters a new volume. So in the last video, we just spit it out, or we spat the screen, just the information, the step. We saw its position and its volume, and we also had the velocity set to 1, but we could also just put this down to 0 and run it again. Remember, we don't need to compile because all we're doing is changing the macro. We're not changing the source code itself, so we don't need to compile. So in that case, we just get only the stuff spitted out in the stepping action class, and we don't get any of the track being spitted out because we set the velocity to 0. So but for now, let's just put it back to 1. So let's say we want to actually get some quantity stored. So let's, for instance, say we want to look at the average energy of electrons which are produced, and regardless of how they're made. So if we go to stepping action, it would be helpful if we could just store the energy what are we doing? The kinetic energy of all the electrons that are created. So not the primary electron, but just secondaries. So one way we could do this is just creating a simple variable. So let's go to our header, and if we open our stepping action.hh, then if we just go down to the private, so if we make a variable, and let's just call it mean, okay, we're doing mean energy of electrons. So let's just go mean KE, and we'll go elec, and let's have an integer to store the number of electrons created, so number of elec. So let's just copy those two variables which we're defining in the header, and then we will need to then initialize them when the stepping action class is created. So that's when we move to the stepping action constructor. So this function gets called every time the stepping action class is created, which is at the start of the run in the main, or technically it'd be the action initialization class. So if we just set this to 0, and similarly we set the number of electrons to 0 here. So now we've got our variables set to 0. So let's go, before we got it printed, no, let's go here. So we've got pre-KE, so let's just comment out the, let's get rid of the post step, and let's get rid of the volume name for now, and just get the stepping number and the parent ID. So hopefully you remember when we were running, so let me just run the electron macro again. So hopefully you remember with the track ID that the primary particle, so the particle which we shoot ourselves, so an electron with 1 MeV, it always has a parent ID set to 0, and it has a track ID set to 1. So, and any secondary particle which is created either from the parent ID itself or from some other secondary particle which then creates another secondary particle, then it takes a parent ID based on the track ID which it was created from. So any particle which isn't the primary the primary particle will have a parent ID which isn't set to 0. So if we wanted to access only electrons with energy, if we want to access only secondary electron energies, we could just use an if statement. So if we were to just go if, and we want to check electrons, so secondary electrons, if we just use parent ID, and we want a parent ID not set to 0, and so this would be executed every time it's a secondary particle, but we only want electrons, so we could also, if we ran this, we might also get gammas stored or something like that, but we just want electrons, so we'll also say and only execute if the particle name is an electron, and in that case for Geant4 the electron name is E-, so this code will execute whenever the particle is a secondary electron. So let's go this is a secondary electron, and exclamation because we're very excited, and let's spit out the kinetic energy of the electron, and we'll do the pre-electron energy. K was, so remember there's a pre and a post step, and the post step's pretty much the current step. So if every time the electrons, or anytime the step's called, if we want what it's currently, the kinetic energy currently is, then we use the post step. So we'll just go PE and post KE. And where's our code here? Oh, sorry, that's a variable. So I assume I've also got it as KE. And for now, we'll just comment out all of this, I think. So let's just compile that, see if we did anything wrong. And we'll probably get a lot of warnings here because for the stepping action stuff, variables we're creating but aren't used, so that's why we get so many warnings there. So if we run it again with the electron macro, so we see nothing spitted out to the screen, but as in outside of the stuff that's being spitted out due to the tracking verbosity of 1 in the electron macro. But when we go to our secondary electron here, so parent ID set to 1, then at the step ID of 1, remember we don't access the step when it's created at step ID 0, it's always the step ID of 1 when the stepping action is called. So we get this message being printed out. This is a secondary electron, and the kinetic energy was 0.01946 blah blah blah. And actually, while we're talking about this, one thing I should point out: whenever you're printing out and it actually matters what you're printing out. I'll just make sure I haven't already hard coded here. Then if you don't specify the units, then Geant4 will just decide what units it thinks are the best. So in this case, it looks like it's doing MeV, but if it's some crazy low energy or crazy high energy, it might pick different units. So it's always good to specify, especially when you're actually storing quantity. But for now, it looks like it's just doing MeV. So in this case, we're lucky that it's storing the same, the same units as the verbosity information. So if you go back to step ID 1 and look at all the stuff which is being executed by the stepping action class, we see that this is secondary electron because parent ID is not equal to 0. And we see the kinetic energy was 0.019, and that was when it was created. And if we compare that to what the kinetic energy of the electron was for actual step ID of 1, it was 156 MeV, sorry, 0.0156 MeV. So then we see with the stepping action printing out K is 0.156. So you see, again, the post is based on the current, and the pre is the, the pre is the step before it. So you see we've got this for every step in this case, but if we just, so you can see when we've got step ID equal to 1, as in when we've got the stepping action first calling, that we can get its energy that it's created at by just, if we added the step ID equal to 1. So let's add that now. So let's also have step ID, so what do I call it? Step number. So if the step number is equal to 1, then execute this code here. So let's just recompile that. And just run our macro again. So in this case, we only see the stepping action being called once. I was just making sure we didn't have more than one electron. And in this case, we've got our energy when it's generate 195. So that's all good. But let's say, we were running, instead of just one particle, we want to do 1,000 particles. And this isn't exactly, you wouldn't want to manually add up energies by looking at the output of a simulation. So what we could do is use these variables we created at the start of the video. So let's just copy mean K electron, and we'll go mean K electron is equal to pre-K, and then we'll have number of electrons plus plus. So remember what all this syntax means in C++ is this plus equals symbols is equivalent to this statement here. So it's just a more concise way of writing this. So plus equals just means the variable plus some other quantity to the variable. So these two statements are equivalent to one another. I'll just do with the concise method. And similarly, the plus plus just means increment the variable by quantity of 1. So then at the destructor of the stepping action, so this function gets called when the stepping action class is deleted or removed, and this is near the end of the simulation after all the particles have been tracked. So we could spit out the mean electron. So let's say mean K of secondary electrons was and what do we want to do? Have our mean K electron and divide that by number of electrons there. In fact, and I'll just be safe from a software point of view. So in case there's no electrons created, no secondary electrons created, then our number of electrons will just be 0. So I'll avoid dividing by 0. So I'll just have this. In fact, let's make this all safe. and put this in here so it's only spit it out if we actually have something. And let's be fully safe and have an else statement. So if number of electrons isn't greater than 0, then we'll just say Geant4 Cout, there were no secondary electrons created. And let's do a sad face, because that would make us very sad. So let's compile that again. Oh, and while I'm thinking of it, we'll have this output in units of MeV. So let's just make that again. And run it. Just see quickly. So here you see our run ended here. And then this is where the destructor or the stepping action class is actually called to be killed. And that's when the code we just added is called. So the mean K of a secondary electron was 0.194, and which is the same here. And actually, let's also add Geant4 Cout, the number of secondary electrons created was equal to what the variable called number of elec, and G4 and L. So make, and let's just run that again just to double check everything. So number of electrons 1, good. So now let's just move it to testing with 2 electrons. So always good to move in incremental steps rather than shooting a million particles only to realize you had some silly incrementing of your variable or something like that, and just gets broken. So so here's our first electron, our primary particle electron, and a secondary particle which was generated here, so 1946 again. Then we've got a secondary parent, secondary primary particle being fired again, and no electrons was created there, and again that looks good. Let's just move it up to 5 primary electrons being shot. So, oh, sorry, I don't need to compile because I'm just changing the number of electrons in the macro. So let's just see how many we got. So we had 2 secondary electrons that time, and let's look here. So parent ID 1, parent ID equals 0. So that was the parent particle, and here we've got parent ID equal 1. So this is secondary electron. So got an energy of 0.29 there. And what we got here, another primary particle, parent ID 0, parent ID 0, parent ID 0, and here we've got a parent ID equal to 1, so we've got a secondary electron. So 0.19, and then there's our first primary particle. So 19 and 2, what was the other? So 29 and 19, so about 0.03 and 0.2, so it's about 0.25, yeah, so a bit under 0.025, so that looks like that's making sense. And let's actually go to our physics list and decrease our electron from 10.3 3 millimeters to 1 millimeter and see how many electrons we got. So you see here, for instance, we got a lot of ionizations occurring, but because the energy of those ionizations was so low, we didn't actually get those tracks created because they were below the production threshold, so all that energy was deposited locally. But once we decrease the energy of production by 10 times, we see we've got a lot more electrons now, so we've got 17. So here we've got lots of secondary electrons being created with much lower energy. So here we've got 0013 and 004, 0015, and here we see we've got a parent ID of 4. So in this case, the track ID of this particle was 4, so this would have been a secondary electron created from another secondary electron. So if we actually wanted a, so track ID 4, so this is the parent particle of this track, and you can see where this particle was created. So 372 in the X and 87, so what was the energy? So it's one of these ionizations, but I can't be bothered staring that long for that case. But so now that we've lowered the production of secondary electrons, let's just, and our code seems to be working pretty well, like nothing too unexpected. So let's now just get rid of our our verbosity in the run action, since, where are we? Run electron.mac. So let's put that down to 0 so it doesn't spit out everything. Let's shoot 100 electrons. And in the stepping action, let's how many did we get? 17. So I guess we get 170 lines printed out. So that shouldn't be too long. So we'll keep it like that. No, I didn't change anything. So let's just rerun that macro with 100 particles. So we'll get quite a few times the electron was created. And you can see lots of these, the primary KE and the current kinetic energy, lots are set to 0. So you see that this electron, which is created with a much lower energy than what we first had it set to. So in our physics list, when we had it set to 10 millimeters, we were only generating electrons with a fairly high energy. But now that we've gone down to any electron with a range of 1 millimeter is created, so now the electrons which are created there's quite a lot of them that are quickly absorbed or have too low of an energy. They have interaction which caused their death quite quickly, compared to what we had initially. So let's just go to the end output. So the number of secondary electrons created was 330, and the mean kinetic energy of secondary electrons was 0.006, and that should be MeV if we were being diligent. So let's just, for the future. So that's one way we could store just one quantity, and that's kind of, it's kind of helpful if you just want a quantity such as some mean energy or the number of particles generated or something like that. But if you wanted to look at a spectrum of electron energies, then this way wouldn't be very helpful. You'd have to do it slightly differently. And in the next video, I'll be showing you how to do that using root.